Okay, so today we're going to do derivatives of exponential functions. So positive thing, we moved away from trig functions and inverse trig functions. And now we get to look at doing derivatives of exponential functions and some background information before I get into that. Few of them being trig still. But these are ones that you have explored when we first learned limits. So you should know that this answer is 1 and this answer is 0. So now we're actually at number 3. And this expression is actually very similar to what you see in number 2, except instead of cosine theta, it's e to the h. So we want a graph to evaluate this. We'll do this one graphically. Here we go. Okay, so I did this one on paper and I wanted to add it. So this is what the graph of y equals e to the h minus 1 over h looks like. And you can see that there's a hole in our graph when x is equal to 0, or I should say h is equal to 0. Okay, so you can just replace this with x's, and so we have the x-axis. Or you could say that this is h. Ta-da! And when h is 0. So we can't just do the direct substitution because it's a hole in the graph. But as you can obviously see, the limit exists. There's a limit from the left-hand side and a limit from the right-hand side, okay, is reaching the same height. And as far as my drawing, because, well, I'm not an artist, it may be hard to see. It may be really close to 2, but it is 1. So I'm going to box that off. So, yeah, so this is another one of the limits that you kind of need to memorize, just in case it comes up. But we actually also need it so we can take a look at deriving our formulas for when we're dealing with exponential functions, okay? Our most popular function for, well, exponential functions is y equals e to the x, but it's not the only exponential function. The base e cannot be e, our natural base. It could be 2, it could be 3, it can be any positive integer. So with that being said, we can extend our derivatives to learn not only what it is for e to the u, where u can be any exponent, chain rule, you need du over dx, but also if it's a to the u, we need to incorporate that ln of a and then take the derivative of our exponent. So I do tell students to memorize these. As far as writing down notes right now, just memorize it, but I'm going to start deriving it, okay? And when I start deriving it with our limits, at least for this one I will. Okay, you could kind of skip through the video so you could get to the example problems that I have, kind of shorten our lesson, and always go back to see, well, where did it come from? How did this formula kind of get about? So there we have it. Okay, so you could jump to example 1 at this point once you copy down all your notes. And so if not, this is where you would want to see the derivation. Okay, so like I said, we're going to start with the first one. And so the limit of e to the x plus h minus e to the x, so we're using a definition of the derivative here, over h as h approaches 0, okay, can be rewritten as e to the x times e to the h, because remember, same base, you add the exponents, so you have to know those rules inside and out, backwards and forwards, minus e to the x over h. So you may notice that within our two terms, we can factor out an e to the x. So that's what we're going to do. Sorry, that was an arrow before. So now we can actually use our limit properties, not derivative properties, but limit properties. And say we're multiplying these two things together. Okay, we are. That's this. So we're taking the limit of each. So the limit here we had said or discovered in the last slide that it is 1. We're going to write that this is 1, but I'm running out of space. Okay, so I'm just going to bring it over here. That's times 1. And if we were to look at this expression, okay, there is no h to substitute, so it's just e to the x. So that's actually like our final answer once we're trying to like take our limits. So now, if it's not just x, we need to do chain rule. So I'm going to replace the x with a u and say it's e to the u du over dx, which is what we said here. Okay, so that's where the derivative comes from. Okay? All right then, so we have an example 1, pretty small example 1. So example 2 is a little bit lengthier. So easily jot down example 1 as I start reading it. So at what point on the graph of the function y equals t 2 to the t power, I'm sorry, I didn't think that was a tongue twister until I had to read it. I'll try again. While you copy, y equals 2 to the t power minus 3. Okay, so that graph. At what point does the tangent line have a slope of, and I'm missing the word of, but that's okay, 21. All right, so here we go. We're going to take out our equation and write it out. I'm not going to read it again just in case I mess it up another time. And we're going to take the derivative with respect to t on both sides. Okay? So this, I already took the derivative on the left. I'm going to take the derivative on the right. There are two terms. The derivative of negative 3 is 0. So I'm just concerned about the 2 to the t power. So this is like that a to the x power. So dy over dt is going to be 2 to the t ln of 2. Okay? So that's our rule. And the derivative of t is 1, so you don't have to worry about the du over dt part of the formula. So now we want this to equal 21 because we know that tangent line has a slope of 21. So that's the next part of our problem. So hopefully you can follow this. This is our derivative that indicates the slope of the tangent line. We want it to be 21, and I'm running out of space. All right, so I'm going to just kind of bring this up here. All right, we need to isolate our exponential because that's where our exponent is. So we're going to divide both sides by the ln of 2. That is a number, by the way. And to get rid of our base of 2, what we do in pre-calculus and calculus, we use our natural log, okay? So we want to say that we have the natural log on both sides. A common log will also work, but we use natural logs here. And the reason we do this is because, and I need some space, we have the properties of logs to kind of break up and get that exponent by itself. So one of the properties of logs is that if there's an exponent, you can bring it in front of the logarithm. It's got to be a logarithm, by the way. It can't just be anything. So I'm just rewriting the right side of the equation. And now you can divide both sides by ln of 2. So t is exactly the ln of 21 over ln of 2 divided by the ln of 2. It looks like we really love ln. Well, it's true. We do. But if we need a more approximate value, this is easier to work with. T is approximately 4.927. Okay, so that is the point that we have for t, right? And if we needed the y value, Oh, this is not coming out good. Let me rewrite this point. Okay. We'd plug it back into our original function, and we end up getting 27.295. Always our answers to 3 decimal places. Okay, and that's it. Okay, so we figured out what t is. By the way, you can also expand on this logarithm as well if you'd like. This is right here, the ln of 21 minus the ln of ln of 2. But when our calculator comes in handy, we don't really need that extra step. All right? So either way, it'll work. Let me know if you have any questions. Now we're off to example number 2. Okay, so example 2 is lengthier. You're going to see a lot of word problems with exponential functions because, well, exponential functions represent either exponential growth or exponential decay, which is a natural process that we have in life. And that's where you see Euler's number used more often. All right. This may be familiar to some of you, or at least the concept here of the flu spreading, because there was a pre-calculus problem with a different function here. Or it could have been the same function, but I think I remember a different function, very similar type of question. So the spread of a flu in a certain school, sorry for getting cut off here, is modeled by the equation P of t, where P of t is the total number of students infected t days after the flu was first noticed. Many of them may already be well again at time t. A, estimate the initial number of students infected with the flu. B, how fast is the flu spreading after 3 days? C, when will the flu spread at the maximum rate? What is this rate? All right, so let's try tackling each one of these. So in part A, we need the initial number of students, so that's when t is 0. So we just plug that in. If you're copying the problem, just copy the important information, the function, what P of t represents, what t represents, etc. So remember, substitution is the most powerful thing, and we end up getting an approximate answer because we are dealing with Euler's number here. So we say that it's 4 students or 5 students. The AP exam will probably write down that it's 5 students. They do round, like we learned our rounding skills in math class. I know it's a long time since we learned rounding, but you can say 4 students. Sometimes in their rubrics they will talk about being lenient and how you round it. So this is not really yet 5 students, but yet we round it to 5. All right, so we're up to part B. B, we need dp over dt because it's asking how fast is the flu spreading after 3 days. This is very similar to talking about velocity. So we need the derivative. So dp over dt needs to be found. And what I did is rewrite my fraction, so I'm not using the quotient rule, because with a constant numerator, it's more likely you're working with 0 once you take its derivative. So I end up just rewriting this so I can use the power chain rule. Okay? So I get negative 100 times the quantity of 1 plus e to the 3 minus t power to a negative 2 power. Then I multiply the inside, which has an exponent, so there's another inside of negative 1. So it's 2 times the chain rule. All right, so now I'm just going to rewrite dp over dt. Sorry about that. I didn't mean to go up on the video. All right, let me just erase. I didn't mean for you guys to hear that, but you already did. So, At least this video is hysterical. I'm making mistakes left and right. I'm coughing. I can't speak. I was trying to read the problem before, and it just wasn't coming out. All right, dp over dt is 100 e to the 3 minus t power over the quantity of 1 plus e to the 3 minus t power, but that's squared. Okay, so you probably get this if you did the quotient rule. So now I want to be able to plug in 3 for t and see what I get. So you actually don't need to rewrite this as I did here. But I was just trying to be neat, and now as I say this, I look at my handwriting. Not really neat. I apologize. That's supposed to be an E. Oh my goodness gracious. Please forgive me. All right, so this actually works out to a nice number because we get 100 over 4. And that means that it was 25 students per day. Students. Why can't I write students here? Students per day. Students per day. There we have it. And we're up to C, and I'm losing my voice. Okay, so that time I remembered to stop the video to cough. All right, so C. When will the flu spread at the maximum rate? And we talked about our relative min or max being where your derivative equals 0, okay? Because that slope of the tangent line would be 0 when there's like a min or max. When we get to working with derivatives more often, this will be very easy to remember. All right, so we want to set this equation, so let me make some room, equal to 0. I will put it up here where we have a variable. Equal to 0, and we stop. So now we cross multiply with 1, and we get zeros equal to 100 e to the 3 minus t power, that was a 3. And we go to solve, that was supposed to be an equals. And to get the variable by itself, we could do ln on both sides. But we have a little bit of an issue. 3 minus t cannot equal the ln of 0 because the ln of 0 is not defined. Think of its graph. Okay, y equals the ln of x. It never touches the y-axis where x is 0. Okay, so if it's not defined, we need to see if there is still a maximum on the graph for our function. And believe it or not, there is. I'm going to see if I can pull it up, but I'm going to write the answer in the meantime. So remember, we got 25 students a day, so we can adjust our y-scale to include that value. And it turns out that it was 3 days that we had the 25 students per day. So that's when the flu sped at the maximum rate. Okay, and this, from our last part, was our maximum rate. So I'm going to try to see if I could go over that with you. Let me know if you have any questions on its graph. But there we have it. Okay. So make sure that you practice, and good luck.